Hello, S4 students. Um, I've got a lesson online today for you guys. This is a tough subject that we're going to study today. It's conductor ampacity. Um, this is a subject that we're going to build on for the next 3 to 4 weeks as we progress through this class. This is where our code class turns into more of a code calculation class. So you're going to want to make sure that you got a calculator, make sure you got some pens or pencils with you. If your code book is not tabbed, you're going to want to take those pens or pencils and stick them in the sheets in between the pages so that we can easily flip back and forth in our code book because we're going to be primarily focusing on 2 to 3 different tables today, so a lot of flipping back and forth. Typically, this is the point in class where I'm looking at you guys and you're scrambling to pull out a highlighter, so if I could, I would let you borrow my highlighter. All right, so we're going to jump into my PowerPoint here. Hopefully this helps you guys learn. And then I'm also going to post a second video where I'm going to do some demonstrations of some practice problems. All right, so again, this is going to be Article 310, which is Conductors for General Wiring, the second part, Lesson 2 of our code class for Chapter 3. All right, so the learning objectives for today are to discuss the effect of heat on a conductor's ampacity, discuss heat containment and heat dissipation in accordance with the installation of this conductor. We're going to use table 310.15b16 to determine the conditions of use that affect conductor ampacities. We'll determine various adjustments and correction factors and apply those factors to calculate conductor ampacities. And we're also going to calculate conductor ampacities under varying conditions of use. So we got a lot going on this lesson. Okay, so before we start talking about conductor ampacity, we got to go back to the basics and understand what ampacity is. And this comes out of Article 100. Ampacity is a term that's created from 2 words, pretty much. Ampere and capacity. So ampacity is basically the measurement of electron capacity of a conductor, or the maximum number of electrons which can safely travel down that conductor at the same time without heating it up and taking it past its temperature rating. The material, insulation, and size of a conductor, they play an important role when determining total ampacity of a conductor. You guys know, obviously, as our conductor is larger, it's able to handle more current. And as that wire is smaller, obviously less amount of current. We will use NEC tables to determine the total ampacity of a conductor. Each table is different because heat from the conductor will be dissipated differently depending on the installation method. So the first thing I want you guys to do is, why don't you flip in your code book to table 310.15b16. The first thing I wanted to point out was that the different sizes of conductors that we deal with. Typically 18's the smallest. A lot of times we're not using 18's because that's really small and cannot handle a whole lot of current. So normal house wiring we'll see anywhere from 10 to 14 gauge. And you can see as I begin to go down that scale in your code book, 18 to 16 to 14 to 12 to 10, you can see the actual conductor size gets a little bit larger, a little bit larger, a little bit larger. all the way until we get down to 1. The sizes that I'm referring to are the AWG sizes. This is American wire gauge. And after 1, as we begin to look at larger conductors, they actually switch the numbering system and they go to a aught, 1-aught, a 2-aught, a 3-aught, a 4-aught, or 0, 00, 000, quadruple 0. After a 4-aught, we switch to thousands of circular mils, which is actually the physical size of that wire. So 250,000 circular mils, 300,000 circular mils, 350,000 circular mils. Our code book recognizes all the way up to 2 millions. That would be the largest size conductor on that table 310.15b16. So first thing I wanted to point out was, obviously the larger the conductor, the more current it's going to be able to handle. And we'll see that especially in all 3 different columns. There's a 60-degree column, a 75, and a 90 degrees Celsius column for this table here. And just take a look in your code book as you begin to go down this chart. You can see that the conductor ampacity begins to increase significantly. There are complex formulas that can be calculated to determine total ampacity of conductors, or they can be found using tables and basic adjustment and correction formulas. In this lesson, we're not going to take overcurrent protection into consideration when determining conductor insulation and sizes. Next week, we're going to find out that the terminals that we are actually landing these conductors are usually the weakest link in our system. But I'm not going to jump the gun on that, so that'll be for next week. Again, Article 100 defines ampacity as the maximum current in amperes able to continuously carry the load under the conditions of use without exceeding its temperature rating. Most conductors will have an insulating jacket that surrounds the conductor, and most of these insulating jackets are made from plastic. Unfortunately, this material will degrade much faster than the actual conductor inside of it. The maximum temperature permitted is determined by selecting insulating materials' ability to withstand those temperatures during the entire length of the cable. So if one portion of your cable is getting heated up because it's in an attic or on a roof, we got to treat that cable on that condition of use for the entire length of that cable, not just that one little section. So what would be the heating sources that actually would cause these conductors to heat up? The first one would be area heat. So this would be the heat, just the ambient temperature in the location where these conductors are installed. Load current heat, we know as current is as long as electrons are flowing on our wire and current is flowing, we're going to produce heat because there is no such thing as a perfect conductor. We know each one of these conductors does offer a little bit of resistance, and over the length of that cable, it will heat up as more current flows. Also, adjacent conductor heat. So if you have multiple conductors inside of a pipe, those are all trying to get rid of that heat from the current flowing on that wire. So that's also going to affect it. and the ability to cool down or dissipate that heat. If it's trapped inside of a pipe, it may not be able to dissipate as easily as something that's run in free air or something like direct burial cable. Conductors cannot be heated beyond their limit. So we're going to take a look at some of the different jackets that we typically work with in the field. The most common that I remember installing when we were, had any normal installation in EMT conduit was typically THHN or THWN2. And what those letters stand for are different abbreviations. You can see in this slide here, T stands for thermoplastic. If there's an R in those abbreviations, it's usually a rubber jacket. X is thermoset, so it's cross-linked. S would be silicone. H is heat resistant for 75 degrees C. The double H would be high heat resistant, so this is a high heat jacket, 90 degrees C. If there's a W in it, it's water moisture resistant. N stands for nylon jacket. MI is mineral insulated. This is a special type of a cable, kind of a pain in the butt to work with. MTW is machine tool wiring. You'll see this a lot of factory installed panels will have this machine tool wiring, like control panels. That -2 tells me it's 90 degrees C dry or wet location. So when I put them all together, like I said earlier, one of the more common jackets that are out there is THHW. That would stand for a jacket that's got a thermoplastic jacket, high heat resistant, and water resistant. So where can I find all this? This all comes out of table 310.104A. So if you flip to that, again, it's showing an example of two different types of jackets on these conductors. The first one, THHN. If I am looking in that table, I can see that the letter type is THHN. The trade name is a high heat resistant thermoplastic. Under the application provisions, it says it can be used in dry and damp locations. The insulation is flame retardant, high heat resistant thermoplastic. And it looks like they've got different sizes, all the way from 14 to 1 millions. The second type would be, so again, before I leave the THHN, we would identify that as its maximum operating temperature. We would say that that would be what's considered a 90 degrees C conductor. Our RHW is a thermoset conductor. It is also a 90 degrees C wire. Oh, I'm sorry. Scratch that. I was looking at RHH. Rewind. RHW is a moisture resistant thermoset. Without the -2, it is just a 75 degrees C conductor. Can be used in dry and wet locations. It's got a flame retardant moisture resistance thermoset jacket. And looks like it comes in sizes 14 all the way up to 2 millions. So that's just an example of how I can figure out, based off of those abbreviations on my jacket, what my maximum operating temperature is of that conductor. Since conductors are placed in various applications and installed in various conditions. Temperature corrections and adjustment factors um, need to be applied to the ampacity of that selected conductor to make sure that the insulated conductor temperature is not exceeded. So we have to, if it's installed in a really, really hot location, we have to make a correction. So back to that table 310, 310.15b16, you can see at the top, this table is actually named allowable ampacity of insulated conductors rated up to and including 2000 volts, 60 degrees C through 90 degrees C, not more than 3 current carrying conductors in a raceway, cable, or earth based on an ambient temperature of 86 degrees. So at 86 degrees Fahrenheit, all the ampacities of these conductors are listed on this chart here. But anytime we get outside of that 86 degrees or have more than 3 current carrying conductors, we need to do one of 2 or maybe both adjustment and correction factor, where we actually derate or lower the amount of current that this cable can handle. Something else I wanted to point out was there are multiple tables. So if you flip the page to table 310.15b17, the conditions of use change a little bit. Now it says allowable ampacities of single insulated conductors rated up to and including 2000 volts in free air. So maybe something like cable tray, that would be considered free air. I know at the refinery and even out at the steel mills, they're installing a lot of, cable tray. Table 310.15b18. This table is used 150 degrees C through 250 degrees C, so really, really hot, high temperatures, with not more than 3 current carrying conductors in a raceway cable based on ambient air temperature of 104 degrees Fahrenheit. And then there's 19 and 20. 20 is supported on a messenger based on ambient air temperature of 40 degrees C. So the most common one we're going to use is 310.15b16. So I would have this one highlighted in my book and be able to use this chart here. Here is the table 310.15b16. So here's all my different sizes, 18s being my smallest, 2 millions being my largest. Here's the different temperature ratings of the jackets, 60 degrees C, 75, 90, and this would all be for copper conductors. On the right side here, this is for aluminum conductors, a 60 degrees C jacket, 75 degrees C jacket, and a 90 degrees C jacket for aluminum. So most of the time we're going to be working out of this column, or this column here. I don't know about you guys, but most of the time when I was on the job, we were pulling copper conductors, unless it was really, really large service equipment, or it was in a bad area and they were worried about the copper being stolen, so they could potentially switch to aluminum, where scrap value is not worth as much. So let's do an example where we manipulate this chart. Common wire THWN-2 and size number 6. So the first thing I have to do is look at these charts. I can see that a THWN-2 is a 90 degrees C conductor. And I said number 6. So the allowable ampacity if this was installed in a conduit with no more than 3 current carrying conductors and an ambient temperature of 86 degrees, that cable would be good for 75 amps. But what happens if I exceed that 86 degrees, or I've got more than 3 current carrying conductors in a pipe? Well, then I'm going to have to use these next 2 tables. The first one is table 310.15b2a. So when we're doing a correction for temperature, I'm going to use this table here. So first I have to know what the ambient temperature of the air is that let's say my conduit run was located in. And so if it is, sorry guys, if it's 104 degrees and I've got a 90 degree C conductor, that 75 amp conductor is no longer that number 6 that we use an example for. I would have to take 75 times 0.91, and now that conductor would only be good for 68.25 amps. And we're going to do some examples here in my next video, so don't get freaked out if you didn't pick up on that right away. So I just want you guys right now understanding how to manipulate this chart. Here's my temperature in Fahrenheit. Here's my temperatures in degrees Celsius. Then the next thing I would have to do is look and see what is the temperature rating of the jacket I'm using and find where those two intersect. 90 degrees C, 104 degrees Fahrenheit, 0.91 is my multiplier. This table here is if I have to make adjustments for more than 3 current carrying conductors in a pipe. Let's say I've got a couple networks. I've got 6 conductors, two networks inside of my pipe. I then have to derate that cable to 80%. If I've got 7 to 9 conductors, it then gets derated to 70, 10 to 20, 50, 21 to 30 is 45%, 31 to 40 conductors derates down to 40, and 41 and above is 35% of that allowable ampacity. So you can see it really becomes a problem as soon as we get past 9 conductors. This is one of the reasons why we don't want to jam our conduits full of wires, is because they're not able to dissipate that heat when we've got a lot of current flowing on them. And over time, that heat wears on that jacket, and that jacket becomes brittle and breaks away. So, next time you guys are pulling wire, make sure that you're paying attention to how many conductors are inside of that pipe, because you could significantly be affecting the allowable ampacity of that wire. All right, guys, that's it for this lesson. I'm going to do some practice problems here in the next few posts that I put on YouTube. So I hope that this wasn't too confusing for you guys. We're going to take it in small bites, and we're also going to start off next class by doing a few more of these practice problems. So make sure you guys are doing your homework and you're staying up to date on Moodle. We'll see you guys in the next video.